Assalamualaikum warahmatullahi wabarakatuh. We are from Group 3 of Thermodynamic Group Assignment. As you guys can see on the screen, today's topic is vehicle engine. So this is our group member. First, ELISSA DAHLIA. Second, me, I am Nur HAZIQAH. The third person is MOHAMMAD IFTEKHAR and Azraf Idromi. As an overview, the first law of thermodynamics is the conservation of energy principle. Energy can be neither created nor destroyed, it can only change form. Conservation of energy is in an isolated system, the total amount of energy remains constant. Here is the visual for you guys to see the energy before is equal to the energy after. For the equation, Q equal to delta U plus W, where Q is the heat transfer, delta U is change in internal energy, and W is work done by the system. Application of first law of thermodynamics. For the first law, the application of the conservation of energy principle to heat and thermodynamic process. The kinetic energy of a moving car is converted into heat energy at the brakes and the tire surfaces. The motion takes place with no input energy. It converts energy into mechanical energy. How the vehicle engine works? So the solution is 4-stroke engine, where the first one is intake, where air fuel mixture is drawn in. The second is compression, where air fuel mixture is compressed. The third one is power, where explosion force piston down. And the last one is exhaust. Piston pushes out burn gases. Graphic that you can see for the vehicle engine. That's all from me. Thank you.
The Carnot cycle. Carnot cycle is a theoretical thermodynamic cycle that describes the maximum efficiency a heat engine can achieve when operating between two temperature reservoirs. While an ideal Carnot cycle is not directly applicable to real-world vehicle engines, the concepts derived from it provide insights into engine efficiency and performance. On the right here, we can see the graph of the Carnot engine and the Carnot cycle, and the right of that, we can see the temperature reservoirs, and on the far right, we can see the Carnot engine efficiency formula. Now for the applications of the Carnot cycle. The Carnot cycle operates most effectively when there is the greatest temperature difference between the two temperature reservoirs, and similar to this, a car's engine can operate more efficiently by raising the temperature during combustion and lowering the temperature of exhaust gases. The Otto cycle's compression stroke compresses the fuel-air mixture, increasing pressure and temperature. Combustion efficiency increases with compression ratio. To prevent engine knocking and maintain reliability, there are practical constraints. Engine blocks, exhaust gases, and cooling systems lose heat. Reducing these losses boosts efficiency. Insulation, combustion chamber shape, and modern cooling systems reduce losses. The Carnot cycle assumes a frictionless engine without mechanical losses. Real engines, however, lose energy owing to piston friction, bearing friction, and auxiliary system energy. Lubrication materials and component design improvements reduce these losses, improving efficiency. Recovering exhaust heat increases efficiency. Turbocharging and exhaust gas recirculation gives hot air exhaust gases to improve combustion efficiency.
Thank you to IFTEKHAR. I will proceed the presentation with the application of second law in vehicle engine. First of all, we need to know the definition of second law. Second law thermodynamics states that heat always moves from the hotter object to the colder object unless energy in some form is supplied to reverse the direction of heat flow. Another definition is not all heat energy can be converted into work in a cyclic process. So, the application of the second law in vehicle engine is Kelvin's statement. It is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. No heat engine can have a thermal efficiency of 100%, or for a power plant to operate, the working fluid must exchange heat with the environment as well as the furnace. The impossibility of having a 100% efficient heat engine is not due to friction or other dissipative effects. It is a limitation that applies to both the idealized and the actual heat engine. As we know, thermal efficiency is very important for the heat engine. Thermal efficiency represents the fraction of heat, which is QH, that is converted to work. We can calculate the thermal efficiency of heat engine by using this formula: net work output over total heat input, or also known as W net dot out over Q in. Another formula we can use 1 minus QL over QH, where QL is the heat correspond to the lower temperature and QH correspond to the heat at high temperature. That's all from me.
Alright, thank you Elissa for the basic. So, right now I want to explain about the reversible heat engine. So, reversible heat engine operating between two heat reservoirs have the same thermal efficient that depends only on the temperature of the two heat reservoir, regardless of the working fluid, and no heat engine can exceed this thermal efficiency. So as you can see here, the formula given is the delta dq over dt equal to 0. So, and the regarding, you can get the qh over the th equal to ql over the tl. So the next is the irreversible heat engine. So for the irreversible heat engines, the operating between the same reservoir as in the reversible heat engine as the previous one. So irreversible engine are the ones that undergo loss of the energy in due course of operation, as the losses in the case of an irreversible engine present. So naturally, its efficiency will be less as compared to reversible engines, the previous one, as you can see. And next is the Clausius theorem and equality. Okay, alright. I will explain a little bit the diagram. The integral in the illustration above or the diagram represent the change in the entropy. So for entropy for a complete cycle of the heat engine, so we need to recognize that integral as an entropy integral could be confusing, because you are probably aware that the total entropy must increase for any irreversible engine cycle. So, but this a change in entropy describe what happened to the engine itself, and carries the idea that the entropy on the output side, so the given to the environment, so by the engine in an irreversible cycle is always greater than the entropy added to the engine. So it is consists with the general understanding of the entropy in the second law of the thermodynamics, that is always increase for an irreversible process. So the equal sign in the clauses inequality above applies only the ideal or Carnot cycle, because since the integral represent the net change in entropy. So the Clausius inequality applies to any real engine cycle and implies a negative change in the entropy on the cycle. That is the entropy given to the environment during the cycle is large than the entropy transfer to the engine by heat from the hot reservoir. In the simply heat engine, where the heat QH is all added at the temperature TH. Then an amount of entropy delta S equal to QH over the TH is added to the system and must be removed to environment to complete the cycle. So therefore more heat must be dumped to the cold receiver to get rid of this entropy. So this leave less energy to do work. So as you can see here, the reversible heat engine that can absorb heat from the reservoir head and constant temperature are shown in the figure below. So the change in entropy over a whole cycle a heat engine is shown by integrate in the image side, right? So I think that's all for me. Thank you. We are impressed with your ability to follow this lecture, which is not necessary entertain for many in your field. Your time and effort is much appreciated. So thank you.